My dear students, in the previous class we understood some of the mathematical relations and basic concepts which are useful to solve numerical problems. So now directly I am going to solve some of the numerical problem. Before going to that, you must know how 1 AMU is equal to 931.5 mega electron volt. So we know that Einstein mass energy equation, that is E is equal to mc square, where m is the mass and c is the velocity of light, and the value of c and m is given by c is equal to 1 AMU. So its mass is equal to 1 AMU is nothing but 1.66 into 10 to the power of minus 27 kg, and c, one atomic mass unit, is equal to this one, and velocity of light is equal to 2.998 in 10 to the power of 8 meter per second. If you substitute the value of this m and c in this equation, so we have substituted, and so we have got, so E is equal to 1.4925 in 10 to the power of minus 10 joules. So now we have got the energy in terms of joules, but we have to express the energy in terms of electron volt. So for that we know the relationship between joules and electron volt, that is 1 electron volt is equal to 1.602 in 10 to the power of minus 19 joules. So we know that 1 electron volt is equal to this much. Then what about 1.492 pi 10 to the power of minus 10 joules? So it can be solved as like this. So 1.492 pi 10 to the power of minus 10 divided by, so 1 electron volt, that is 1.602 in 10 to the power of minus 10. If you simplify this, so finally we are going to get, so 0.9316 in 10 to the power of 3 mega electron volt. So this can be simplified as, so 1 AMU is nothing but 931.6 mega electron volt. So it is also needed, so during solving numerical problems. So let us consider the first problem. So dear students, my suggestion to all of you is, before going to solve the problem, you pause the video. As soon as the questions appear on the screen, you pause the video and you read the question carefully. So once you read the question, so in the left side of your book, so you have to solve the problem along with me. While solving the problem, get ready with the calculator and pen and paper. So after reading a question, you have to write the given in the left hand column of your book. So and you have to identify the suitable mathematical formula which is needed to solve this problem. So let us go through this problem. Tin 108 as tin, you just observe the laser point. Tin 108 has a half-life of 10.3 minutes. A radioactive sample contains 72 gram of tin 108. Determine the mass of tin 108. So tin 108 is nothing but, it is the name of element. Its mass number is 108. That's why we call as tin 108. So determine the mass of tin that has decayed and that has not decayed after 30 minutes. Dear students, the question is very simple. So we have a radioactive tin. Its mass, its half-life is 10.3. So write the half-life. Its half-life is given. So 10.3, T of is equal to 10.3. Write the given. So now, so using this data, we have to calculate the amount of tin disintegrated after 30.9 minutes. Then amount of tin remained after 30.9 minutes. For example, so the radioactive reaction is started. So the mass of tin is 72 gram in this stage. As the time goes on, what happens? This 72 gram is decreases. So let us observe this picture carefully. So before the mass of before the reaction, so the mass of tin is 72 gram. So it is at the 0th minute. As soon as the reaction start, what happen? So we know that half life of this is 10.3. So after 10.3 minutes, so half of the value, that is 72 gram, is 36 gram. That is 36 gram of tin is decayed. That means it undergo nuclear reactivity, and remaining 36 gram is in undecayed state. This is what at exactly 10.3 minutes. So further, again 10.3 minutes, this 36 gram. So what is half of this 36 gram? So 18 gram. So 18 gram is decayed. So 18 plus 36, 54. So after 10.3, that means after 20.6 minutes, 54 gram of tin is undergo nuclear decay and 80 gram is remains. Then again after 10.3, why I am taking 10.3? Because here 10.3 is the half-life period of the given radioactive elements. So exactly at this time, the half of the initial value get reduced. That means before it is 18 gram, to reduce 18 gram to 9 gram, it take half life, that is 10.3 minutes. So again, that's why in every interval of 10.3 minutes, I am goes on reducing half of the initial value at that particular point. So beginning, there is a 72 gram. This 72 gram to convert in 36, it take 10.3 minutes. Further, this 36 gram reduced to 18, again it take another half life. Again 18 gram to reduce to 9 gram, it take another. Totally it take 3 half life. So this is nothing but N. What is the 1 half life? So that is 10.3 is the half life. So what is the total time it can take to reduce 9 gram? It take 30.9 minutes. So at 30.9 minutes, so now this is the final state. So at 30.9 minutes, so 63 gram of tin is undergo nuclear decay and 9 gram is remaining. This is what the solution. Okay, in the problem, he is asking that, so how much of radioactive tin is decayed after 30.9 minutes? Up to 30.9 minutes. So for example, up to 30.9 minutes, so 63 gram already decayed. So what is the total amount? Totally we have 72 gram. So among 72 gram, 63 gram is decayed. So 72 minus 63 is equal to what? Is equal to 9 gram. So finally we can conclude that, so the tin undergo radioactive decay, its half-life is 10.3. So after at exactly at 30.9 minutes, 63. So you just look at here. So 63 gram of tin has decayed, it undergo nuclear reaction, and 9 gram is remaining. So dear student, are you understood? Okay. So now the next problem. It is related to a mass defect. So I will read the problem. Calculate the mass defect binding energy per nucleon for carbon 12 whose isotopic mass is 12.38 AMU. The masses of neutron and proton may be taken as 1.0084 and 1.00894 AMU respectively. So dear students, so this is a mass of neutron and mass of proton is given. So you know mass defect. So write the given. So here he has given. So mass of carbon 12 isotope, that is capital M he has given. He has given capital M, and he has given mass of proton, that is MP he has given, and Mn he has given. So what we have to calculate is, Mn is the mass of neutron. So we have to calculate the mass defect, that is delta M, and binding energy per nucleon. Before going to solve any numerical problem, you must clear what he has given in the problem and what we have to identify in the problem. So this can be solved as follows. So solution. So this carbon 12 containing 6 protons and 6 neutrons. So atomic number is 12. So this is a mass number. 12 minus 6 gives 6. So you know how to identify the number of protons, neutron in a given nuclei. So the atomic number is nothing but proton. If you subtract, so if you subtract Z from mass number, it gives total number of neutron. If you want number of neutron, just you have to subtract atomic number from the mass number. That means A minus Z gives number of neutron. So there are 6 protons are present. So mass of one proton is 1.00894. If you multiply, you will get this value. And mass of neutron, there are 6 neutron. Each mass is 1.0084. So we get 6.0553640. So this is the total mass of individual nuclei. So we know mass defect. So mass of C12, and we also know the mass of C12, that is 12.0038. So then mass defect is given by, so total masses of nuclei, so this value minus this, so it gives 0.10024 AMU. So this is a mass defect. Then binding energy is nothing but what? So mass defect, if you multiply mass defect with 931, dear students, here I am not writing the mathematical formula here. You have to write while solving. So binding energy is nothing but, so you have to multiply the mass defect with 931.6 mega electron volt. So you have got 93.38 mega electron volt. This is the binding energy. Then binding energy per nucleon. If you want to binding energy per nucleon, you have to divide, so total binding energy, so divided by total number of nucleons. Here the total number of nucleon is 12 for carbon. Nucleon means including both proton and neutron. You know binding energy per nucleon. So total number of proton and neutron, so is 12. So if you divide this 93.38 by 12, so you will get 7.78 mega electron volt. So this is the binding energy per nucleon. So next problem, again here also we are going to calculate binding energy. So calculate the binding energy per nucleon of iron 56. Okay, actually the iron 56, 26. Its atomic number is 26, mass number is 56. So given the mass of iron is 55.93 AMU, mass of neutron he has given and mass of proton has given. So we know so in iron Fe, so its atomic number is 26, mass number is 56. So it has 26 protons and it has 30 neutrons, and so mass defect is nothing but, so this is the numerical formula ZMP. Here Z is 30. We know the value of Z and MP, A minus Z and Mn. Substitute all the value in this equation. So you will get this equation. Then if you simplify, so you will get 0.52846 U. This is the mass defect. So now we have to calculate binding energy. So therefore binding energy is nothing but what? So delta M into 931 mega electron volt. So delta M is nothing but 0.528461 into 931. So this is 491.99 is the binding energy of iron. And the binding energy of nucleon, the total number of nucleon is 56. If you divide this energy by 56, so you will get 8.785 mega electron volt. So dear students, just by looking the question, first you try to solve. So after that you cross check your result with these answers. Next class I am going to continue this.